Okay, so I hope it's working.
Yeah, go ahead.
So hey everyone, my name is Pranshu Malviya, and yeah, I'm going to present this paper called Manifold Metric, a loss landscape approach for predicting model performance. So this work was done in collaboration with Jerry, Quinton, Aristide, and Sarath. So yeah, starting with the main motivation, like the new models, like training new models from scratch is quite expensive. With the coming up scaling laws, we have all the large models coming in, we have more data, which basically will lead to better performance. That's basically the trend right now. But training these models from scratch is what is very time consuming. So there should be some alternative ways. One of those ways is basically to can we expand a pre-trained model and then continue the learning process? This will be very efficient. It should be a function preserving expansion as well. Like we want to transfer the knowledge. Uh, it is also cheaper as compared to like training a whole new model from scratch. But so in this work, we are mostly going to focus on like how do we expand the models in such scenarios where you have ever expanding the size of the data. So the one thing about model expansion is it is definitely useful, but it's not very well understood. And there are several works in terms of like explaining what does expansion really does on your loss landscape. For example, there are some theoretical works which basically showed that like over-parameterization is basically not the elimination of bad local minima, rather it is elimination of a bad basin. And the way people have shown is in this way, like you have multiple local minima appearing in a say under parameterized model. When you expand it or when you basically add more parameters, those local minima still stays, but it's the basin which is which is relatively more connected. So that's the main idea that we are going to use to be able to uh, understand if we can come up with a good type of expansion. Uh, so yeah, so basically it leads to an increase in global minima manifold. There was like again, this is another example of a paper which basically showed that like uh, the over parameterization basically leads to the increase in global minima manifold of the loss landscape. So basically, more connected minima there are, easier it will be to train through your optimizer. So yeah, basically this is the main idea that we are going forward with. Right. So yeah, so we are going to use geometric properties of the loss landscape and to predict the impact of expansion. And the way we do it is like we are going to propose a metric which is ideally should be independent of optimization process. It should be computationally cheap, and it should be reliable across different architectures. And the reason that we pick this path of understanding the properties of loss landscape is because of that fact. Like it should be reliable across different architectures. Yeah, so that's basically the main idea that we are going to go ahead with. Yeah, so starting with the approach. So we call this as a manifold metric. As I said, like the manifold is basically we are going to use this. We are going to define this metric as using these two concepts, permutation invariance and linear mode connectivity. So what we do here is imagine a graph from a pre-trained model. Imagine a graph with nodes which are defined by functionally equivalent networks which are generated by permuting neurons. So permutation invariance has been like known well-known property in the neural networks, where what you do really is imagine you have a MLP with a single hidden layer. You pick the first and the third neuron in the hidden layer, and then you basically swap their positions. So this is you just pick, what you're doing really here is like you just pick these two neurons, swap their positions. So in the loss landscape, the properties of this new network, which it will be basically functionally very equivalent. in terms of the loss, the locality around this point where the model really lied in the landscape, but it will be at a different location entirely uh, in that in that loss landscape. So that's basically the idea of like that's what we basically mean by having multiple nodes basically representing multiple models which are lying in some kind of a minima. Uh, so we have a pre-trained model, so that's why we have a one base node which will assume that lies in a minima, and by permuting neurons, we are going to generate these different types of nodes. And yeah, so these are kind of the nodes in the graph, and then how do we connect them? How do we define the edges? So that's where we are going to use linear mode connectivity. So again, linear mode connectivity is a I'm going to explain what exactly it is, but if basically if the barrier size, which is the difference between the interpolation between your loss and the models, if this barrier size is basically below a certain threshold, then we call them a linearly connected uh, minima. So what exactly the barrier size is? It's basically defined by the greatest difference between your loss of linearly interpolated networks and their and their losses. Yeah, so so basically like this again has been well known in the literature, as in people have tried to find a pair of solutions. Either you can get those solutions from different initializations. You train the same model from different initialization, you arrive in a certain kind of minima. If you try to connect those two minima, you'll generally arrive at a higher loss surface. So uh, this point, basically, if you can follow the cursor, it will represent the barrier between these two minima. However, if you train the model from same initial point, and at some step k, if you create another copy of model and train it using a different seed, for example, there are chances where your two models will end up in a same kind of a basin. And this by same kind of basin, I mean that you can basically connect these 2 points, using a low loss barrier. So this will basically have a low barrier, a very small value, ideally zero. But yeah, so if the way we are going to use this concept for manifold metric would be like, we have nodes which we have for which we have instead of training a new model from some kind of some case step separately, instead of this we are going to use the permutation invariance property, where we permute a certain subset of neurons, so that we jump like the new model will basically lie in some other part of the landscape, but we will have a very similar property. So if your first base model was a minima, you permute those neurons, that will also have the same kind of properties. And we are going to compute the barrier between those 2 points. So yeah, that's basically, and the way we define the edge is like if you have this barrier less than certain threshold lambda. So this lambda is a hyperparameter. So I'll again describe like what we are exactly going to do is basically you start your model, you train your base model from scratch. If you train the model such that like you arrive at theta 1, which we assume will be a minima as a pre-trained model, we compute different permutations like theta 2 or theta 3, theta 4, and so on. We compute the barrier between those points, and if those barriers are less than lambda, that's what we are going to basically count. So the manifold metric here, we define it by m, will be a function of your current theta, which here it is theta 1, lambda, and n. So lambda is a hyperparameter, and n is basically the number of permutations that we are going to generate. So these two are the main hyperparameters in our metric, which will define like how flexible it could be. So yeah, so the main hyperparameter here would be lambda. Like it will differ from like lambda basically will define your barrier size, right? So it will differ from one model to another, one data set to another, and so on. So this is I'm going to basically describe like what exactly how exactly lambda will play a role here. So the overall picture, the overall idea here is we count the number of edges that ended up being like uh, between those nodes that ended up being linearly connected, or more like almost linearly connected, because we have put this lambda as some non-zero value. If this lambda was zero, then we are putting our constraint of they have to be linearly connected, these two nodes. But yeah, uh, so if the nodes are well connected, we say that they belong to a manifold, because uh, if they are well connected, you'll have almost you'll have more solutions lying in a same loss basin. They belong to a same that's when we say that they are belonging to the same manifold, which was easier to find. And by easier to find will be like if you have multiple minima in the same basin, your optimizer will be able to navigate to a good solution faster. So yeah, so that's the main idea of like what this manifold metric really is. Now coming back to our main motivation, like I'll go back to that, where why would it help in expansion? So so for expansion, what we do is like we expand the model. Like let's assume we are expanding the model just by going from some pre-trained model phi prime to theta, and going from one model to another. I mean, like just imagine like we are just adding one neuron in your hidden layer, right? So what we do here is for the base model, we collect all the barriers, we compute all the barriers between like all the nodes that we generated. Again, there are 1 to n, like n defines the number of permutations for the nodes. We compute the barrier in between them, and we pick the baseline threshold, lambda, as some q quantile of this set of barriers, right? So suppose like q was 0.5. So whatever the median of this set was, that's what we are going to take our baseline threshold lambda. And all of this is computed on the base model itself. We haven't expanded yet. So after we expand, what we are going to do is we are going to compute this difference between this metric. So we are going to compute these, the metric again being like the number of edges that we found to be less than number of edges we found to be, satisfying the linearity constraint, like the below lambda threshold. So we are going to compute this for the bigger model theta with the same baseline threshold that we defined using the base model, right? So you can understand it as a like this is a relative metric, and if you think about it, like the second term will just be q here, because we are just computing the ratio of how many edges did we end up finding from the overall possible number of edges. So and we picked Q as like the quantile of this, some qth quantile of the set. So basically, we ended up replacing lambda as a hyperparameter to Q, which will again be a hyperparameter, but this will be much more useful or more like flexible in our case when we test it on different types of models. So for instance, like if you have the base model is simple MLP with one single hidden layer, so yeah, just assume that we are adding one more neuron. If your base model is trained on some data, you compute this Q. Based on this Q, you compute this lambda. Like what are and once you get this lambda, it will give you some notion of, okay, what's the relative quantity that you really look for the barriers when you expanded the model. So from our initial, like from some of the initial like plots that I showed you, like when you even add one single neuron, you end up expanding your minima manifold. And once that, basically you'll have more minima connected, if you can imagine a loss surface. Uh, and if that happens, your overall given this baseline threshold, which will be ideally higher in case of smaller network, for the bigger network, ideally, the number of edges that you'll be able to find for this bigger model should be more. That will be the ideal case. That's the intuition that we have here. Because you have more connectivity in your across your minima in the bigger model, this threshold will be set such that the number of edges that you will be able to find, the number of connectivity between those minima in that bigger model that you'll be able to find will be more as compared to the base model. So that's the main idea, and that's how we are going to define this manifold metric. Yeah. So is there a question right now, or can I move ahead?
No, go ahead.
Okay, so what are the main implications of this? Like, so this is a very like all of this was mostly like looking at what people have done in theory in terms of how over parameterization really affects the overall loss landscape. The way like some of the implications of this would be like with higher connectivity, it has been also shown that higher manifold connectivity has been linked to better generalization. And there is a really famous paper on this, which basically suggests that you'll be able to find a winning lottery ticket if you have this higher connectivity in your surface. Then what the metric really represents is a more of a average smoothness of the loss landscape. So it's not exactly sharpness as because like sharpness is more of a local property, uh, but this is more about like the terrain that exists between the solutions. So it's not just the slope where you stand. Like it indirectly measure how the roughness or smoothness really look like in your loss surface. And our idea was basically like, as one of the previous papers also showed, that just simple adding one neuron will make the surface relatively more smoother. So that's what our idea was to apply here. Yeah, and more importantly, like it will bring, of course, bring training stability. More importantly, like it's a zero cost proxy. What we are proposing here is a metric, which is a performance predictor. So, and the way we are going to use it is like we just need one single batch of the data of whenever you want to expand. We just take a single batch of the data, we compute this metric, uh, it only requires a few forward passes. And remember, like the number of nodes that we had, uh, which was controlled by the hyperparameter n, that is going to define the number of forward passes that you need to do, because ultimately we want to compute those barrier sizes. That's what is defining this metric. So the higher the n is, the number of the more the number of like passes that you'll have to get. But you don't need any backward pass, so you don't need to train at all. It's just about computing the barriers. We have like in the paper, you can also look at like how we are exactly doing that. I'm not going to get into that in that much detail, but yeah, like uh, since this is a zero cost proxy, you don't need to train anything. You don't need the backward pass or computing, Hessian and all. This basically lies in the bucket of, some set of metrics which are well defined in neural architecture search. So there are different types of, like there are many types of these metrics that predicts like the performance. This metric particularly lies in this bucket where you have like Synflow, Jacobian covariance, grad norm. Like people actually use grad norm as a metric to predict what kind of performance your model could get to. And here the purpose is to have a metric which will tell us among a list of candidate models how which candidate model will be able to perform best just by computing this just by using this set of forward passes. So yeah. Um, sorry. Sorry, Razvan, is there a question?
Sorry, I just wanted to say you have like maybe 1 minute left. If you
Oh, okay. Okay. Okay, so I'll go through the experiments quick. Like since we have all these different zero cost proxies already existing in the neural architecture search, we basically compare our metric with these, where we found out that like we basically train a small base model, as I said. We get the whatever the best validation performance from that base model. Then we we have we have this like set of candidate models of expansion. So for example, like that candidate model can be just adding one neuron, or it can be adding one whole layer, or can be adding uh, both like layer and more set of neurons to increase the width. We have this candidate list of expansion models. We train them to get the best performance that they could have gotten. Uh, now, and then we compare the performance difference that the expansion resulted in versus whatever the metric suggested us for that candidate. So here we are basically showing the correlation between your M0. M0 is basically, without training, what was the what was the number that manifold metric basically assigned to that candidate model, and the GT star, which is basically the best performance that the expanded model could have gotten. And as it turns out, like for these different kinds of setups, we have like manifold metric performing consistently better. Well, it's not really high in case of ResNet, but compared to other metrics, it's more consistently positive. So that's one of the main results that we had. Like without even actually training the model, the manifold metric was able to predict which candidate is going to perform the best across these setups. Again, like the assumption here is that you have a base pre-trained model, and that's what you want to expand uh, to get the best out of the data set, right? So that's one. Then I can probably go over this analysis a bit more quickly. Basically, like what we have here is we just expanded like the layer one width of a CNN while training for CPAR10. What really happens when you train a bigger mod, you train a model after an expansion. So for example, I'm showing the performance gain here and the manifold metric, how it evolved really during the training. So you expand the model such that, as I said, like it should be like we use net to net, which is a popular expansion method, which also is function preserving. So you start with that. You train the model. The performance decreases in the first few epochs, and then will ultimately increase to like after like 500 epochs to some nice percentage. So here the performance gain is around like 8 or 9% itself for the biggest model. But one thing that you'll also notice here is like if I had expanded by adding 24 more channels in the first layer versus 32 more channels in the first layer, they both perform almost the same. So there's a plateau there. So that's what the manifold metric, although it has like some standard deviation, it is able to recognize that. And the correlation basically also looks pretty much positive all the time as compared to SOTLE, which is again another learning curve based metric, which is simply sum of the training loss, which is kind of cheating. So it does involve like training the model to be able to get positive correlation. But you can see that like without even training, the manifold metric had positive correlation with the final performance, and the final performance is those star-based things. So yeah, and we tried this again with when you expand width and depth as well. Here in this particular experiment, we wanted to see that is it just pure expansion, purely adding more neurons? That's basically indicating the expansion or the increase in the value of the metric, or what is it exactly? So in this particular case, we had the candidate model such that we expand width and depth such that the number of parameters at the end remain the same. So there are so many works that have shown like expanding the width will help more in terms of generalization in some cases, and then depth can also help. But even in this case, when you have the same number of parameters at the end in those candidate models, you'll have manifold metric, which is performing relatively better than all the other cases during the training process. Yeah, so and all the other metrics are uh, like kind of unreliable in this case. Then I'll quickly go over these. We have experiments with ResNet and transformers as well. Like the gap really reduces down. The standard deviation increase here, but it basically just suggests that these are much more complex loss landscape that we are dealing with here. So yeah. And then we also have like,
Uh,
sorry, yeah.
we're really over time.
Oh,
Are there
okay.
more slides?
Yeah, this is probably the second last slide.
Yeah, we need to cut it short. Sorry,
Okay, okay.
because we're running
Okay,
really out of time. Let's
okay.
thank Pranshu for the presentation. And